So today we'll discuss the 37th session on relative velocity. So in this session we will discuss in this and the coming next few sessions we'll discuss the relative velocity collision problems in two dimension for phase 2. Phase 1 and phase 2 has been fully explained in the 34th video on relative velocity. So if you want to know what is phase 1 and phase 2, you just refer to the 34th video on relative velocity. There you'll get all the details of phase 1 and phase 2. So today we'll discuss the 37th session on relative velocity of phase 2, that is the relative velocity collision problems between two points in three dimension, in which the relative acceleration between the two moving points is not zero, it is non-zero. So that we'll discuss, okay? So I'll write down the numerical and we'll discuss it by several methods, okay? So I'll write down the question. Three points P1, P2 and P3 are initially situated at the three vertices of an equilateral triangle of side length L. These 3 points simultaneously begin to move with same constant speed v. Such that st meaning such that at any instant velocity of p1 is directed towards p2. That of p2 is directed towards p3 and that of p2 is directed towards p3 and that of p3 is directed towards p1. Now in this problem we have to determine two things. Find first the time after which the 3 points meet. The time after which the 3 points meet by several methods. And second thing, we have to find the polar equation of trajectory of point P1 and all the 3 points, not only P1, P1, P2, P3, all of them. The polar equation of trajectory of 3 points P1, P2 and P3 with the pole at the center of triangle. At center of triangle and reference line parallel to P2, P3. Okay. So this is the question. So we'll discuss this problem today in this 37th session on relative velocity. Fine. All right. So I'll rub this. Fine. So now I'll draw the diagram. Okay. Initial diagram. So at time 0, these 3 points are situated at the vertices of an equilateral triangle of side length L. So at time 0, the diagram will be something like this. This is the equilateral triangle of side length L. This is point P1. This is point P2. This is point P3. This is the center of the triangle that has been taken to be the pole O. This is the reference line which is parallel to the side P2, P3. Okay. Now, what will happen? The 3 points simultaneously begin to move, such that at any instant of time P1 moves towards P2, P2 moves towards P3, and P3 moves towards P1. Always. So how the motion starts? Suppose in dt time P1 comes here, then P3 moves somewhere here, so that its velocity is directed towards P1. And P3 comes here, P2 comes somewhere like here, so that its velocity is directed towards P3. Again, after a short time, P1 comes here, so P3 comes here, P2 comes here. So that at any instant of time, velocities of P1 is directed towards P2, that of P2 is directed towards P3, and that of P3 is directed towards P1. So in this way, at certain instant of time, after start of the motion, P1 is somewhere here, P2 is somewhere here, P3 is somewhere here. Okay, at some instant t. So at time t, we join these 3 points. Now see, suppose at time t, length of this triangle is, side length of this triangle is s. I will just rub it. Okay, I will explain further. Now see, first of all, before solving this problem, we have to make three assumptions, three concepts have to be cleared. 3 points must be cleared beforehand. First, where will the 3 points meet? 3 points will meet at the center of the triangle. Why? Because speed of all the points are same, v, constant. Suppose the points meet at somewhere at time capital T, say. In that time 0 to capital T, P1 must have moved the distance Vt, speed into time, speed is constant. P2 must have moved the distance V into capital T, constant Vt. P3 must also have moved the same distance Vt. So they all meet at a point which is equidistant from the initial three locations of the 3 points. That should be at the center of the triangle. Fine. So what is the first observation? The 3 points will meet at the center of the triangle. Meet at center of the triangle. That is the first point. The second point is this. At any instant of time, the 3 points will form an equilateral triangle whose center coincides with center O of the original triangle. At any instant of time, the 3 points will form an equilateral triangle whose center coincides with center O of the original triangle. Coincides with the center O of the original triangle. So these 2 points have to be kept in mind, okay? The first point is they will meet at the center of the triangle, that is at point 2, and at any instant of time the points will form an equilateral triangle whose center coincides with the center O of the original triangle, that is at time 0. Okay, so this is the basic assumption. Okay, this is basic point which has to be made clear. Okay, I'll rub this. Okay. Now we have to find out first what time the points will meet. So this is the triangle at time small t. Suppose the side length of this triangle is s, as I mentioned just now. Suppose at time t, polar coordinates of point P1 are r comma theta. That is OP1 is r and this angle is theta. This is the unit vector OP1 ER along radial direction. And this is the unit vector E theta. E theta and ER hat are mutually perpendicular, and E theta hat corresponds to the sense of theta increasing. Velocity of P1 is equal to V, that of P2 is also V, and this also is V. This is the situation at time small t. Okay. Now first we have to find out after what time will the 3 points meet. So this will solve by 3 methods. Okay. So method 1. See, method 1 is this. Method 1 is this. See, this is also an equilateral triangle as I mentioned just now. So this angle will be 60 degree total. This will be OP1. This OP1 is the bisector of this side P2, P1, P3 angle. Okay. So this angle will be 30 degree. And OP1 is equal to R. OP1 is just equal to how much? R. Alright. So method 1. Method 1 is this ds by dt. Where s is the side length of this equilateral triangle at time small t after start of motion. This is the time derivative of s with respect to t. This is the rate of change of s with respect to time. Rate of change of s with respect to time, that is equal to rate of increase of s minus rate of decrease of s. Minus rate of decrease of s is the rate of change of s with respect to time. Okay. The rate of increase of s minus rate of decrease of s. Alright. This triangle is equilateral triangle as I mentioned just now. This angle is 60 degree. This is also 60 degree. Now see, Suppose we are observing the side P1, P2. That is side P1, P2 we are observing. We can observe any of the three sides, P1, P2, P2, P3, P1, P3, any one of them. So I am observing P1, P2. Alright. So ds by dt is rate of increase of s minus rate of decrease of s. Now see, rate of change of s with respect to time of this line, side length P1, P2, will only be due to the component of velocities of P2 and P1 along this line P1, P2. The component of velocities of P1 and P2 normal to line P1, P2 will have no effect on the distance change of side length s. Side length s will change only because of the component of velocities of P1 and P2 along this line P1, P2. Okay. So first what we do, we find the component of velocities of P1 and P2 along this line. Now velocity of P1 is v, that is along this line itself. Velocity of P2 is v. Component of v along this line is v cos 60 degree. So I just draw this line side here. This is P1, this is P2. P2 is moving like this v, 60 degree angle, and P1 is moving v along this line. Component of this v along this line is v cos 60 degree, that is v by 2. Now see, ds by dt is rate of increase of s minus rate of decrease of s. Now see, this v will cause this side length to decrease, and this v by 2 will also cause the side length to decrease. So rate of increase of s will be 0. Neither of these two components, v and v by 2, will cause the length of side P1, P2 to increase. It will try to decrease it. So rate of increase of s will be 0. And what about rate of decrease of s? V plus v by 2. 3v by 2. Okay, fine. So this means ds by dt is equal to minus 3v by 2. ds equal to minus 3v by 2 into dt. On integrating this, v by 2 integral dt 0 to capital T. Where capital T is the time after which the 3 points meet. S. Now what is the limit of s? Initially s was just equal to L, and when the points meet, distance between any two points P1, P2 will be 0. Now integral ds L to 0 on integration, we get minus L. V is constant, so this is outside the integral anyway. By 2 into T. Meaning T equal to 2L by 3V. This is the answer by method 1. Alright. So the points will meet at the center of the triangle after time t equal to 2L by 3V, beginning from the start of the motion. Alright. This I have discussed by method 1. Alright. I love this, okay. Method 2. Fine. Method 2 is by using the concept of relative speed of approach. By using the concept of relative speed of approach. So now we can take any of the three pairs P1, P2, P2, P3, P1, P3. You can take any one of the three pairs. Alright, suppose we take the pair P1, P2. Suppose we consider the pair P1, P2 pair is considered. Suppose we consider the pair which one? P1, P2. Suppose we consider the pair P1, P2. This P1, P2. I'll draw this here again, okay? So this is P1, this is P2, this is S. This is the velocity V, 60-degree angle, the velocity of P1 V along this line. So first what we do, we observe P1 from P2, okay? So what we find, we will find the velocity of P1 with respect to P2. So V, P1, P2, G. G meaning ground frame. V, P1, P2, G meaning V1G minus V2G. Relative velocity of P1 with respect to ground minus relative velocity of P2 with respect to ground. This is just V, sorry, okay? So this is just vector V1G, that is this one, this V, and minus is just reverse of V2G. V1G plus minus of V2G. So reverse and add. The velocity of P1 with respect to P2 is the vector sum of these two velocities. This V1G is this V. V2G is this. Reverse of V2G is this. This will also be 60-degree alternate angles. So this V1 P2G is the vector sum of these two velocities, this and this. Now what is the relative speed of approach of P1 with respect to P2? Relative speed of approach of P1 with respect to P2. See, P2 will say, observe that velocity of P1 is vector sum of these two, this V and this V. P2 will observe that relative velocity of P1 is the vector sum of these two velocities. Now, the relative speed of approach of P1 with respect to P2 is the speed with which P1 will observe, P2 will observe P1 to come towards it. So from this you see, relative speed of approach of P1 with respect to P2 is the sum of components of these two velocities along this direction. That is component of V along this direction, which is V cos 0 degree in V, and component of V along this direction, which is V cos 60 degree in same direction. V by 2 cos 60 degree is half. Relative speed of approach is 3V by 2, which is a constant. So relative speed of approach of P1 with respect to P2 is how much? 3V by 2 constant. So this means separation between the 2 points decreases at this rate. So rate of decrease of S with respect to time is 3V by 2. Alright. So rate of decrease of S with respect to time is 3V by 2. Now rate of decrease of S will be written as mod of ds by dt. Alright. Mod of ds by dt. That is the rate of decrease of S with respect to time. I'll run this. Okay. So, what we see, as time passes by, S decreases, meaning S is a decreasing function of time. Therefore, ds by dt is nothing but minus ds by dt. Therefore, minus ds by dt is just 3v by 2. So, again, we get the same equation as you got in method 1. So, if you again integrate it, we get the same time. So minus ds is equal to 3v by 2 into dt. On integrating this, 3v by 2 integral over dt, 0 to capital T. Initially s was L, finally s will be 0. On integrating and inserting limits, we get L. This is 3v by 2 into T. So T is equal to 2L by 3v. This is the answer which you get by method 2. The relative speed of approach of P2, P1 with respect to P2 is 3v by 2. And integrating with the required time by method 2 also. Fine. So by method 2 also we get the same time. Is it alright? Now I rub this, okay? Now method 3. Method 3 is this. See, consider this original diagram. This OP1 is equal to R. OP1 is just equal to R. This is the velocity V of P1. V. It makes an angle 30 degree with the line OP1. Sorry. Okay, yes. V makes an angle 30 degree with the line OP1. E theta and ER as defined just now. See. So, we know from the theory of cylindrical coordinate system. Cylindrical coordinate system you will get in the 6th, 7th and 8th of kinematics of point. 6th, 7th and 8th video of kinematics of point in a plane. Okay. Then you will get the cylindrical coordinate system, all details you will get there. So I will use that result. See, velocity of P1 with respect to ground is just this velocity V along P1 to P2. That can be expressed in cylindrical coordinate variable as VR ER plus V theta E theta hat. ER and E theta are unit vectors as defined just now. Now this VR is the radial speed of point P1. Radial speed. Radial speed of point P1. That is the component of Vp1g along ER. Component of Vp1g along ER. And that is from the cylindrical coordinate system, that is dr by dt. So V is this 30 degree. ER is this one. So Vp1g makes an angle of 150 degree with the vector unit vector ER. So this component will be written as V cos 150 degree from the definition of component of vector of a vector. Yes, V cos 150 degree. Cos 150 degree is minus root 3 by 2. So we get this. This means dr is equal to minus V root 3 by 2 into dt. Now we integrate this equation from both sides. 0 to capital T. At time 0, the points were here. At that, R will be, initial value of R will be OP1. And from the geometry, you know that OP1 is L by root 3. So lower limit of R will be L by root 3. And when the 3 points finally come to O, R will become 0. Upper limit of R will be 0. On integrating this and inserting limits, this we get minus L by root 3. Now V root 3 by 2 is constant, it comes outside the integral. Integral dt 0 to capital T. So now I complete it here. So minus goes away. So simplifying this, we get how much? 2L by 3V. Same answer we have obtained in method 3 also. Alright. So we get the time t as 2L by 3V. After time t equal to 2L by 3V, the 3 points will meet at the center O of the triangle. Alright. So I have demonstrated this problem by 3 different methods. Now we have to find one more thing. What is that? polar equation of trajectory of these 3 points, with point 2 as the pole and then this line as line through and parallel to P2, P3 as the reference line. Okay. So we have to find the polar equation of trajectory of P1 and P2. Now I'll grab this, okay. Now we have to determine the polar equation of trajectory of these 3 points. That is part B of the question. So consider point P1. As I stated just now in the method 3 of first part of the question, velocity of P1 with respect to ground is this V. That has a component along ER and component along E theta. As I found just now, dr by dt is just minus V root 3 by 2. This is just the radial speed of point P1. VR, okay, radial speed of point P1 at time t. Similarly, velocity of P1 is this, it has a component along E theta, that will be, this is 30 degree, this is right angle, so this is angle is 60 degree, V cos 60 degree, V cos 60 degree, that is V theta, that is the orbital component of velocity of P1. Orbital component of velocity of P1, and that is the component of V along E theta. Vp1g along E theta. Now Vp1g is this, E theta is this. This is 30 degree, this is 90 degree, this is 60 degree. So component of Vp1g along E theta will be V cos 60 degree, that is just equal to V by 2. Also we know from cylindrical coordinate system that V theta is equal to R d theta by dt. So we get the equation R d theta by dt is equal to V by 2. So from this we get dt is equal to 2R by V into d theta. And from this equation we get that dt is equal to 2 minus 2 by V root 3 dr. dt is equal to minus 2 by V root 3 dr. These two dt's are same, so these two should also be same. Therefore we get 2R by V d theta 2 by V root 3 into what? dr. Now V and V will go away, 2 and 2 will go away. Alright. So now I'll rub this, okay? So 2 by V goes away. So we get dr by r. I'll draw a line here. dr by r is just equal to minus root 3 d theta. Now we integrate this equation. Integral over d theta. Integral over what? D theta. So what is going to be the lower limit of r? This distance initially P1 was here, O is here. Equilateral triangle of side length L. By geometry OP1 will be L by root 3. At time t, r it becomes. Upper limit of theta is just theta at time t. Now lower limit will be theta naught. Okay. So this I'll rub, okay. So this integral dr by r becomes log r basic. So log r minus log l by root 3, that is same as log of r root 3 by l, that is minus root 3 into theta minus theta naught. Value of theta naught has to be specified. It is the initial value of theta for P1. This is base C. So simplified and becomes L by root 3 e power minus root 3 into theta minus theta naught. This is the polar equation of trajectory of P1. So one more thing, at any instant of time, the 3 points P1, P2, P3 will be equidistant from point O. If this is OP1 is R, then OP2 and OP3 both are equal to R. This will also be R, this will also be R, this will also be R. They are all equal. Only theta naught is different for the 3 points. Initial value of theta for 3 points is different. So we have to find the value of theta naught. For that we must take the case of P1, we must take the case of P2, we must take the case of P3. Alright. Now wrap this, okay. So the question arises, how to find the value of theta naught for these 3 points, initial value of theta. So I'll rub this also. This also I'll rub it, okay. See, initially P1 is here, time 0, P2 is here, and P3 is here. This is point O, pole. This is the reference line, line through and north parallel to P2, P3. We join this P1 to O. This is theta naught for P1. So we'll say for P0, for P1, theta naught is just equal to pi by 2 radians. For what about P2? Theta naught will be this angle. This angle will be P2. Theta naught for P2. Now this is 90 degree. This is equal to 90 degree. And this is 30 degree. You alright? This will be 30 degree. Okay. 30, yes. Okay, 30 degree, so 120, okay, 120. The theta naught becomes 2 pi by 3. And for P3, theta naught becomes this angle. Initial value of theta for P3 will be this angle. This will just be 360 minus 30, 330 degree. And 11 pi by 12. R will be common to all 3 of them because they are equidistant from point O at any instant t. Therefore, polar equation of trajectory of P1, that is equal to R barabar L by root 3 e power minus root 3 into theta minus pi by 2. Similarly, polar equation of trajectory of P2, R equal to L by root 3 e power minus root 3 theta minus, for P2 theta naught is 2 pi by 3. And for P3, polar equation will be R equal to L by root 3 e power minus root 3 into theta minus 11 pi by 12. Alright. So this is the polar equation of trajectory of these 3 points. Alright. So this was the 37th session on relative velocity. I have discussed a general problem. It's of great importance, frequently asked in exams. Okay. You carefully go through it. Okay. In the next session, 38th session, again I will discuss one more problem of this type. We'll generalize for the case of n particle system. And we'll take up some more equations on relative velocity collision problems in 2 dimension in which A relative is non-zero. Fine. So I'll close it here itself. Fine. Alright.